No, they gotta make their money if they're gonna keep it free.
Well, I was hoping at least a tech thing.
These are the tech, the political ads are the ones that pay them more money probably. So from a user's perspective, would you rather pay 20 bucks a month for online GDB? Or would you rather I get it, but just for the different languages and the ability to just run it inside of a web page, online GDB is pretty good for a one-stop shop. And if I have to see some political ads, it's then you can just fix it by doing this. And at least it's political ads and not like, you know, random like porn ads or something like that I can't use the thing in class. And I would assume, well, actually probably have ad blocker on here. So ad blocker wasn't blocking, but I don't know, whatever. All right, I started the recording already. We're up here. All right, so I gave you some code last. Let me just start with this. Just give us our deathmatch starting point. Okay. So homework for today was to effectively replace the way we are storing our player 1, player 2 information. Instead of having all these variables, we're going to have a struct of type player and set that player's hit points and player's armor class to the correct stuff, and then modify the rest of the code to work with that. All right. Shouldn't have been a major ordeal, but it forced us to use structs, which we looked at last time. So what we're going to do is up top here, we're going to go ahead and define our struct. I had it up there last class, but so we're going to have a struct called player. You can name it whatever you want. And I'm going to say this struct is going to hold on to a couple of pieces of information. It's going to hold on to int hit points and an int armor class. All right, so that's my my data type that I've defined. All right, so now I have a new type of variable called player that's of type struct that can hold two pieces of information, HP and armor class. So what we'll do up here is we'll go ahead, or down here, we'll create a couple of variables of that type. So we'll say struct player P1, and you can do all this in one line, but I typically like to define my variables on separate lines. So you can say struct player P1 comma P2 if you wanted to. I just prefer to, I'm defining two variables. Let's define them one after another, because I think that if you get too many variables defined on one line, you start getting lost on what's going on. All right, so now when I'm dealing with P1's hit points, I could say P1.HP, P1.AC, P2.HP, P2.AC, like that. All right, so now we're storing information inside of those structs. Same information, we're still rolling the same number of dice for the hit points or armor class. All right, now when we're comparing them, we're comparing P1's hit points to 0 and P2's hit points to 0. We have our attack roll. We're going to compare it against P2's armor class. P2's hit points gets reduced if they got hit. I probably could have just done a search for anything underscore, just replaced it with dot, and I would have gotten it done. That would be the line before that. What line is that? 28? Oh, I'm still defining the variables. I already defined my variables up here. I no longer need to define integers here. They're already defined inside the struct. I do still need the int for coin. Come on. Is the internet down? I don't have a run or a stop.
I can't get mine to compile.
Oh, like online GDB died?
Well, I can't get, I guess. His works fine.
All right, let me just reload the page. Maybe I need to re-log in. Actually, was I using GitHub or was I using Google? Well, we might be switching over to
There we go.
still have my I have deathmatch in here. I logged in with the wrong account. How do I log out? There we go. Log out. Log in. Let's try a different account. There's deathmatch. But why?
It's fun. And same thing, but I logged out back in.
I just finished logging out and back in twice. Let's save that version. Well, in the meantime, while we see if that finally kicks in, let me just load this locally. So it doesn't matter. Let's call this deathmatch. .cpp. We even know. Oh, there we go. Let's go put it in downloads. Put that in there. All right, so there's the output of our program. Seems to still work. That's the dude that has all of our struct stuff in it. So here's our struct. So we just saw it work. We'll do that later. This guy finally kicked through. Falcon net. Okay. Oh, whatever. Please refresh page to connect. There we go. Maybe it was FalconNet. But in any case, it's running now. So that would have been a reasonable solution to the homework. Just go through and update all the uses of those individual variables with using structs. Now, having said that, what ability does this give us now? Or what does this make easier for us? Now we have the ability to pass structs to functions. So we can have functions that, check to see if a single roll is accurate. So let's look at this. So let's look at if we have a coin flip, a coin is equal to 1. We're doing an attack roll. So we're doing all this stuff. So what I'll do here is I'm going to take that code right there. And we're going to write a function. Maybe called void try attack. All right. And try attack is going to take in 2 players. A struct player P1, struct player P2. All right. I'm going to have to go back and copy that code again because I'm going to copy that to implement it down here. All right, so now we're gonna fill this guy in. I'm gonna just steal this code, which is the same as this code down here, with the exception of who is player 1 and who is player 2, right? So I'm gonna put that code in here. All right, so what does this guy do? This guy, oh, I guess I can. It's a shift tab if you want to move it the other direction. Even though it looks like we're in the middle of a tab there, but I'm just gonna, oh wait, what happens if I do this? That's way worse. All right, that's gonna stay like this. All right, so now player 1 or P1, P2, all this code is happening in terms of them. It's potentially modifying the hit points of these guys. All right. So now all I would have to do up here is if it is, so if we're doing an attack roll against player 2, what did I call my function here? I called it try attack. We would call try attack, passing it P1 and passing it P2. And that would do all of that logic, with a little bit of an exception of who these outputs, what this output is, the player 2, player 1, that kind of stuff. And we'll fix that up. Similarly, down here, and I'm doing the attack roll inside there, not yet. Similarly, down here, let's copy this. I'll just switch who I'm passing in for player 1 and player 2. So now I'll pass in player 2 for player 1. And if you really wanted to look better down here, you can call this the attacker and the attackee or something like that. Then we have to go through and change it and all the stuff down there. But you get the point. These are different variables, different scopes. So P1 here is whoever is currently playing the role of player 1. P2 here is whoever's playing the role of player 2. We dictate that by the order in which we pass in player 1 and player 2 to that function. All right. So now we have something that looks like that. Okay. We're not in a great working place yet. this is gonna where we connect the dots to what we were talking about at the end of class last time with pass by value versus pass by address. Okay, but right off the bat here, what I want us to appreciate is assuming we're rolling in a reasonable direction here, by writing this logic once, the try attack logic once, it's still every bit as, you know, convoluted as it was before, but we wrote it once, hit it inside of a function. But now our main, remember, all programs begin and end with main. Our main method, main function, is a lot cleaner. This while loop is a lot easier to read. As long as P1 has hit points greater than 0 and P2 has hit points greater than 0, as long as both people are alive, attack. If coin is 1, we're going to try attack. P1 is going to try to attack P2. If coin is 2, P2 is going to try to attack P1. So on and so forth. Okay? Makes some sense? All right, but this is just going to do a single attack. So what happens inside here when whoever P1 is attacks whoever P2 is? And if we, let's just go ahead and do it. It's not that big. We're going to call this attacker, maybe attacker and defender instead of attacker and attackee. All right, so we'll have, this is whoever's the attacker and whoever the defender is. So what we need to do is down here, we have to replace all things of P2 with defender. And we would probably want to update this to be, say something else. For right now, why don't we say something like attacker hits a defender. And you're going to see how this then becomes generic, and do we even know who won? But we're going to fix that too. Attacker wins. And this is defender. Okay, good enough there. All right, so if we were to run this right now, let's kind of walk through what would happen. Our coin is going to start off as either a 1 or a 2, based on this roll of a D2 here. So we don't know who's actually going to go first, but as we go through this loop, we ask, are both of these guys still alive? If they are, depending on which coin flip we had, we'll decide who attacks who, who's the attacker versus the defender, the attacker versus the defender. All right, and we'll go back and forth, and we're going to keep doing this as long as both of them are still alive. Now, if we run this right now, it's going to go and it's going to do this just fine. And somebody, let's just assume they get hurt. The problem that we have right now, we saw this last class, is if we pass a struct in as a parameter, that guy is passed by value, which means that when I come in here and I modify the hit points of my defender, like I'm doing right here, this is a local modification only. As soon as this function ends, and this function only goes through one time, right? The attacker tries to attack the defender. He either hits and does damage or misses and does no damage. Those are the things that this function does, right? And it does it one time. We might call that function a bunch of times inside of this while loop, but the function itself takes a swing and may or may not hit. Okay. Now, if it hits, we do adjust the defender's hit points here, but that adjustment is only happening to this local variable. It will not be that we don't have what's called side effect. We will not have adjusted hit points out here. So that means their hit points are always going to remain the same as they originally were, no matter how many times they end up getting hit. You know, do we have any feedback here? Yeah, we have attacker hits defender. So we'll know if somebody's getting slapped around. Okay. But we're going to see that this guy just keeps running forever and ever and ever and ever. And if we want to, you know, visualize it, oh, actually, we're going to be able to visualize it with enough output. Oh, I'm doing it inside of This is the guy that gets us out of our loop before. Remember, we had the should loop. If the dude who just got hit keeled over, okay, if he died, we're not going to loop anymore because there's no more fighting. The problem is that we were using should loop up here, but right now we actually don't need to use that variable. We'll just remove it because when we loop back up, one of the dudes has died and will fall out of the loop naturally. So I don't need this should loop thing. All right. So there's our evidence that it is passed by value because we are passing in the struct of the attacker and the defender. Damage may have been done, but that damage is not being noticed outside of that function because what we were passing in by value. We were giving a copy of the attacker struct and the defender struct. We gave them copies of those guys, and it went and pitted them against each other, and it may have done, a reduction of hit points on one of the copies. But once that function ended, those copies are gone, and we're back to the originals that have their original hit points. They're just sitting there forever. Go ahead.
So could you alter the original value by turning value?
Okay, so good question. So now we have to say, well, so our first question that leads up to that, which she already asked it in her head, was, okay, well, how do I fix this? How do I make it so that the hit points have a permanent change? So one suggestion might be, well, can we just return the modified struct? Whoever was potentially hurt, can we just return that? And now it will have been updated. You certainly could. You could return the value. Let's just do that real quick. So we're going to say that this guy actually is going to return a struct player. That's what he's going to spit out. Now we know inside of try attack, the only thing that possibly was changed in there is the defender. That's our current state of things, right? The attacker swings and misses and nothing happens, or the attacker swings and hits and the defender takes damage. The only possible change that's going to happen in here is the defender's numbers might alter, right? So at the very end of this guy, because this guy's now returning a struct player, we're going to go ahead and return the defender. And we'll do it outside the if statement. So we're going to return the defender whether we've changed it or not. We've told C++ that we intend to return a struct player from this function. That's what he's going to spit out. And I'm going to give you either an unchanged one, like, hey, here he is. Dust him off a little bit, he's fine. Or he's gotten some damage that he's taken. But we're going to hand him back, as you suggested, right? So then what we do up here is we would set P2 equal to try attack, and we'd set P1 equal to try attack. We'd overwrite the defender with the outcome of try attack, because we know that this defender may have a new value when it comes into here. Make sense? All right, so that is one way of getting around it. Okay, so now we see that we have a functioning game, with the exception of we don't really know who lived and who died, right? It's like, okay, well, we were pretty sure there was always going to be an attacker, there was always going to be a defender, and whoever struck the last blow is named the attacker. We don't know who died, is the punchline. Okay, so continuing down the rabbit hole, how do I fix this problem? So first of all, we have a solution to the one problem. We're going to call that not the best solution, but it's a solution using what you know how to do right now. You said, hey, I want to realize the change to those structs. I've noticed that they're being passed by value because those changes are not, there's no side effect. I'm not noticing any change in hit points outside of that function. So somehow I need to get that modified struct out of there. How do we do that? Well, let's just return it and overwrite our original variable. It works. That'll get the job done. But now let's solve the problem of how do I differentiate between my attacker and my defender to know who actually, won and lost. What do you think? Ideas for that? Go ahead.
You have to do something with what the coin is on. That makes sense.
Okay, I'm gonna translate. I feel like you're maybe saying that if we also pass in the current coin, 1 or 2, we can translate that into player who's the current player, who's the attacker versus who's the defender. Okay. Maybe we could pull that off with just a 2-man fight, but obviously we could have battle royales here, right? You know, where we have 1,000 people. Isn't that like how many people are in Fortnite? 100 people? And they're only, why do you know that? You play, don't you? Oh, just he did. I played that game twice. I had one 7-year-old dance over my corpse and I was done. But now I'm getting my revenge. I think I really beat up on like an 8 or 9-year-old in ping pong the other day in VR. That kid had no chance. Just fumbling all over the place. I'm not even that good, but he was exceptionally bad. And I was taunting him. His mom he probably ran back to us like, the guy online is bullying me. I'm nice to them. I compliment their good shots and stuff. And then I destroy their souls. All right. So maybe we could do something with the coin, but that maybe feels a little bit like a hack. Not that you can't do it. Not that you can't do it. Because right now, I mean, the way we're learning programming is we kind of have one arm tied behind our back. There might be plenty of these things where you're like, okay, there's got to be a better way. For instance, like we're talking about with the returning the struct, maybe there's a better way of accomplishing that, but we don't know about it now. So we're kind of, we have our toolkit in front of us and we're just solving the problems with what we know. All right. Other suggestions on how we tell the difference between which players we're dealing with? Player 1, player 2? Good. Yeah. Let's enhance our structs. So we can come up here to our struct. And instead of just having hit points and armor class, we can have string name. And now we don't even just need to call them player 1 and player 2 if we don't want to. Okay, but we will just so it looks consistent. So now we are storing a name in there. So we're gonna have P1 dot name is equal to player 1. And we'll have P2 dot name is equal to player 2. All right, so we're storing a third piece of information inside of our struct. So now, without changing a thing, we're now passing in 3 pieces of information inside that single struct that we're passing into that function. Starting to see the power of structs. Okay, we can pack a bunch of data into a struct and then just say, here's the struct. And I think I mentioned last class that this is our precursor. This is what's going to roll us into having objects. When we start talking about object-oriented programming. So I want you to start thinking along those lines like, oh, that's kind of convenient rather than me having to pass, in this case, 6 individual variables, right? Here's the hit points. Here's the armor class. Here's the name. Here's the other guy's hit points, the other guy's armor class, the other guy's name. Instead of passing 6 different things, we can pass them 2 structs that have everything enclosed in them, okay? Now we're starting to think along the lines of, oh, here's an object with the data you need. All right. So then down in here, what we can do is instead of saying attacker hits defender, we're going to say attacker dot name hits. And there actually we could use a different version of printing here that allows us to put in placeholders as a thing called printf. Actually, I don't want to introduce it now, but it allows us to not have to do as much concatenation here, but we're going to do it anyways. And we could actually do with concatenation, but I'm not going to do that either. So we're going to say defender dot name for that much damage. And then we can say attacker dot name wins. All right, so now depending on who the attacker and the defender is, we're going to have whatever their particular name is. And we're just passing them in a different order each time. And the names then change. All right, so now we have player one wins. Run this again. Player one still wins. Player two wins. There we go. Okay, so going down the line a little bit here so we can pass in additional information to differentiate the two. And now we look at our main. Now we still have this logic here. Now, right off the bat, we might say, well, we used to have all this logic displayed twice, right? We had it inside of main 2 separate times. Well, now at least I only have this chunk of code 1 time. Okay, what's the definition of a function? It's a reusable chunk of code that we write once and can call multiple times. This is generic code. This code operates on an attacker and a defender fighting. And now I can call this code whenever I have an attacker and I have a defender who need to take a swing, attacker who wants to take a swing at a defender. And all I have to do is change who's the attacker and who's the defender. And I can reuse this logic over and over and over again, which then allows my main to be much, much, much cleaner. Make sense? Okay. All right, so now let's go back to the idea of if we have this guy not return anything. So we are going to undo the thing that fixed our infinite loop. Okay, we fixed our infinite loop by returning the possibly modified struct. Okay, so now we no longer are going to get the defender's modified struct. And we won't return it here. So we're back to what we had before, where we know damage is occurring in here, potentially. Damage is potentially occurring in here. And we know that locally, this defender's struct has changes or may have changes happening to it. But those changes are not being felt outside of this function because a struct is passed by value by default. That means we're sending in a copy, you're changing all things to that copy, and the original had no changes made to it. Make sense? That's what passed by value means. I'm giving you a copy, do whatever you want to it, but you don't have to worry, you're not gonna change the original. But in this case, we want the original to be changed. So she came up with a solution of, oh, well, let's just return the value, and that made it work. Not the end of the world, but we're gonna say, okay, there must be a better way. So we'll go ahead and prove this, that we're back to our infinite loop. All right, so because the defender's hit points are never actually changing. So that means that this while loop right here is always going to be true. Their hit points never modify. Okay. So now we want to think about how do we make a difference here? I'm going to go into our slides here. And we're going to talk about pointers. All right, so pay extra close attention to this. Pointers are extremely important, but they're also some of the things that are, I don't know, maybe most intimidating or most feared by programmers for no good reason other than memory seems scary. Go ahead. 124. But obviously that can change because I add slides and remove slides all over the place sometimes. Yeah, it's really inconsistent and I'm sure confusing. And I own that. But it came from a good place. It came from like, hey, here's the material we're going to go through. So this is going to give us a guideline. And then when I want to talk about something, if it wasn't the next slide, I just add it. So that's why you have several things in here duplicated. You get to study it twice. All right. So I apologize for that, but at least before exams, I go through and I tell you what I think is important instead of having you study 600 slides. Go ahead. It's possible. I don't know off the top of my head, but it's possible you could do that. If I fast forward to next fall, well, for all of you, you'll have me for the next class, the 250 class. I'll start with a clean, a fresh slide set. I'll have maybe last year's behind the scenes if I want to see, hey, what do we talk about next? But I'll give you a single slide set that just grows. All right. So remind me next semester so I do that at the beginning. All right. So first of all, how many of you have heard of something called pointers before? Okay. Those are people who've probably had some programming background or maybe at least looked at a lot of things related to programming. Pointers are kind of an interesting thing. And really where they become interesting is how they always exist, but more modern programming languages deal with them differently. So let's start off with what is a pointer? Okay, a pointer is a primitive type built into the language. This is the same thing as bytes, shorts, ints, longs, floats, doubles, booleans, chars. Same thing, same kind of animals, right? These are variable types that can only hold a value. Make sense? So far, nothing scary about that, right? Same thing as an int. Okay. Specifically, pointers hold memory addresses. Okay. And memory addresses become intimidating for us because they are giant hexadecimal numbers and they seem scary. Right? Where we've talked about, I think I talked about it in the context of maybe strings, how memory in a computer works, where our addresses in the real world are much, much more complex than computer addresses. In the real world, your address is 123 Elm Street, you know, in this city, this state, USA, here's your zip code. You have a whole bunch of individual pieces. You can almost think of your address as kind of like a struct. It has a bunch of individual pieces of information that all add up to a piece of information about where you actually live, right? Computer memory, though, everyone lives in one big long street. This is house number 1, 2, 3, 4, 5, 44 zillion down the line that we're going to represent in a scary hexadecimal number. Hence, computer programmers fear, right? And what's funny, what I'm telling you right now is true even in professional developers. And this goes back to something we talked about the first week of class. It's the difference between whether or not you learn to program in a university setting where we don't only focus on the doing, we also focus on the why, theory behind it, versus you do like a boot camp or something like that, where you learn, this is how I use this, not necessarily why it works that way. Now, having said that, that doesn't mean that everybody who goes through a coding boot camp comes out as an idiot. You know, as an individual, if you decide to explore the concepts even more and look into, oh, why does this work this way? You're going to learn this stuff too. I mentioned in here 90% of what you're going to learn outside the classroom. But at the very least, I can throw you an assignment or something like that that forces you to explore something along those lines. All right. Okay, but pointers are, well, memory addresses are intimidating because human beings, we like decimal numbers, and we don't really like decimal numbers when they get too big. We like nice small numbers, like in the thousands or smaller, right? Anything bigger than that, you got to start counting. Okay, is that 100? Is that in the 100,000s, or is that in the millions, or is that in the billions? Or then we start running out of what are they called, right? You know, quadrillions, quintillions, blah 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 blah. All right. I once wrote a iPhone app out of just curiosity for this, and it didn't sell very well. I probably made, I don't know, $70 off it or something like that. But I recorded my voice saying a bunch of like individual numbers, and you could type in a number in there, and then it would read that number out as for the whole thing, like, you know, quintillion, quadrillion, but it would spell it out by piecing together all the audio clips. So I don't know, kind of an interesting thing. You started seeing the pattern in numbers because it is the same pattern. All right, so pointers, primitive type variables capable of holding memory addresses. Just like an int is a primitive type variable capable of holding whole numbers. So far, so good? All right. So now, how do we create a pointer? And what I'll do for the moment, just because I'm probably going to be making some changes to stuff, I'll give you. Does anybody know if I save this and I share it and then I make changes?
It's before you make changes, when you share it is.
So if I give you this link, it'll be stuck in
Yeah.
stone. Okay.
It just gives you the option to view or report. You can't do it.
All right. So I'll give you that as a starting point. Okay. So let's then. You haven't seen that before. This is a multi-line comment.
Yes.
So slash asterisk followed by whatever you want, and then do an asterisk slash at the end, and everything in between is a comment now, which means it won't get run. So right now, all programs begin and end with main. What does main say to do? Yeah, it doesn't say to do anything right now. So if I hit run, hey, at least our infinite loop's gone. So we just have a program that doesn't do squat. We got a bunch of stuff, but doesn't actually call any of it. All right. I want to use this to explore some of our pointer stuff. Now we can create pointers of our different types. We'll talk about what that means here in a second. All right. So if I create an int a and start equal to 5, and I say C out a, we expect this to print out a 5, right? Nothing new yet. Everything's fine. Okay. Well, now what I want to do is I want to get the address of A, where that guy lives. So let's talk about pointer syntax. Pointer syntax, we have an asterisk says get the value that lives at an address. An ampersand says get the address of get the address where a value lives. Okay, so we really have two different syntaxes here. We can say, given a memory address, tell me the value that lives there, the actual value. We could also say, given a value, tell me the memory address where it is in memory, where we stored it inside the computer. So looking at that, if I want to know the address of A, I could say address A. And that's going to give me where it stored that variable in my computer's memory. And what lives at that is the 5. So here's my value 5. This is where 5 lives inside my computer. How did I get that? I asked for the address of A. That ampersand stands for address of. Make sense? All right. So I can create another variable here. And if I want to store a pointer, to store a memory address, we need a pointer type variable. So for example, this is type. Type star var name equals value, let's say. So when we have our variable type, this could be anything we can have variables of, ints, chars, whatever. But we put a little asterisk after it saying this is a variable built to hold the address of one of those. So in this case, I want to hold the address of an int. So I'm going to create a variable of type int pointer. and we'll call it A address just to kind of really drive that home. And this guy will be equal to the address of A. So we've already seen that ampersand A is this integer here, boils down to the memory address where this number 5 is stored. We saw the scary address here, right? That's what ampersand A gives us. I'm going to take that memory address and I'm going to store it inside of a variable. Now I need a variable that's capable of holding a memory address. Specifically, I need a variable that's capable of holding the memory address of an integer. Why is the memory address of an integer different than the memory address of a char?
Chars have like, stored as like multiple, numbers or integers. Because,
Okay. So you're saying chars are different than ints. There's something about chars that make them different than ints. And one of those differences is the size. So right now I just created two variables, int A equals 5, char C equals A. And I'm going to go ahead and print out the address of both of those dudes. And you're going to see our two memory addresses. So I know I want that guy still. See. Why is it giving me the ampersand? I think it's because this is part of the Unicode character set. And it has a static place in memory. Let's just do it with a byte. Byte. Isn't byte one of my types? Good. So two different types of variables. I look at the addresses and I get two memory address looking things. That's the way addresses work. An address is an address. It looks the same. Just like street addresses, if you go down and you look at an address of 10 houses on the street, the format of those addresses is going to look the same, correct? Good.
Like just that whole thing is kind of now type.
Well, this whole thing is a memory address. It's something that looks, well, it is exactly this guy in this case. This guy right here also boils down to a memory address. The same kind of animal, still a memory address, but what lives at that memory address might be different. And let me explain it a little bit where I was going in a second ago. So I said that if you look at 10 home addresses, let's say we're looking at addresses here in Mequon, all the addresses are going to look roughly the same, right? We have the same information that we store when you give somebody your street address. Now, if you go down Elm Street, is every house on Elm Street the same size? Sometimes we have different size houses, right? And certain houses take up a bigger footprint than other houses. They still have a street address, right? 123 Elm Street and 124 Elm Street have the same looking street address, but 124 Elm Street might be a mansion. And 123 Elm Street might be a little shack. If you want to put that into our context here, 123 Elm Street might be a char, which is only 1 byte big. 124 Elm Street might be an int, which is 4 bytes big. So integers are 4 times the size of chars in C++. They're twice the size of chars in more modern languages like Java. Go ahead.
So then when you say value, you're not talking about like but like 1,000 or something. value. That's not that, it's the actual bytes or whatever.
Well, the number 1000. So I think what you're asking here is this. So if we have the integer 1000, we're going to say 1000 is the value. It lives at some memory address. And we're going to say that all memory addresses are the same size. The memory addresses are the same size. If you're on a 32-bit operating system, typically they're going to use a 32-bit memory manager. So your memory addresses are going to be 32 bits, 4 bytes. 32 bits, 4 bytes, those are synonymous, whatever. All right. 64-bit operating system, you're going to have 8 bytes. 64 bits divided by 8 is for 8 bits in a byte gives you 8 bytes. So that's how big the memory address where that guy at least starts is. When I say 1000 is the value, and this is, I think, getting to where what you were asking about. If an int is 32 bits or 4 bytes, 1000 is stored in a, let's say, on a plot of land that is capable of holding 32 bits or 4 bytes of data. And if you remember, we looked at that, that's negative 2.1 billion to positive 2.1 billion. So that's plus or minus 2 to the 31st power. Those are the maximum size values that we can store in 4 bytes. Now, 1000 is nowhere near either of those extremes, right? So if you want to think about what this is going to look like in real life, you have 20 acres of land with a little guest house on it. You own all that property, but you haven't used all of it to store what you want to store there. Go ahead. No, I'm talking about the addresses. The translation you would make is, like I talked about, like our street addresses, 123 Elm Street, 124 Elm Street, 128 Elm Street. All of our addresses are the same thing. They take the same amount of size to describe. The value is, so if we look down Elm Street, all of those addresses are the same size. Every address, if we wrote out the word for an address, they all have the same 5 components. Let's say you have the house number, you have the street address, you have the city, the state, the zip. Just stop with that. So you have 5 pieces of information that go into a memory address or a house address. Now that doesn't tell us anything about the actual house that is built at that address. The house that is built at that address is the value of this. So if we're looking at an integer like 1000, 1000 is the value. That value lives somewhere in memory, and it's going to live at some memory address that looks like this guy. If I printed out 100 memory addresses of all sorts of different types, ints, chars, bools, whatever, they're all going to look like this. Every memory address will look the same. The address itself does not give us any information about the kind of house that's built there. This is the same as real life. So, if I give you the street address of a house, that's not enough information to tell you what that house looks like, how big it is. Are we talking about a mansion? Are we talking about an outhouse? Something like that. This doesn't give us that information because that's not the kind of information this is meant to give. This tells us how to get to the value. Well, that's where we're getting at, where what lives at that address? And we haven't quite gotten there yet, but yeah. The value is the number, like 1,000 is the value, or true is the value, or the character A is the value. Those are the ultimate, those are the houses. As we look down that street, we have a whole bunch of houses that are built, and each of those houses lives at a different address on that street. Okay. Yeah, well, the mansion has a bigger footprint, but it still has that mansion's physical size is larger than the neighbor's house, but the address of the mansion looks the same size as the address of the house next door, even though the physical value, the physical houses are different sizes. That makes sense? Yeah. So, I mean, this does mimic real life, but as soon as we start getting into stuff like this, we freak out, right? Because it's scary. Hexadecimal values are scary. That's part of why I spend time at the beginning of this course doing all that number conversion stuff. So we realize that, hey, this might not be that much fun to do, but we could convert that number to decimal, right? And then it would look even scarier, right? That's just a big old decimal number. Then you got to go and download my old iPhone app, which I don't think is on the App Store. It didn't meet as they got better, it didn't meet the user experience, user interface experience standards that Apple had. But you can go download an app similar to mine that will read that giant decimal number to you, and it's going to be some huge number, but that we'd be able to read in decimals. So it's going to be just as frustrating, right? This memory address isn't all that meaningful to us, with a little tiny exception, and we'll look at it once we see the we'll look at it here probably in like 5 minutes or so as I keep going down this rabbit hole. I just really want to drive the point home for some of these things because, like I said, pointers are something that most programmers find difficult, but they actually are a pretty easy concept if you can just get out of your own fear of giant hexadecimal values. Okay? And keep thinking about it in terms of street addresses. Our human version of addresses are way more complicated than computer addresses are. Good.
So with the int type pointer, is that actually storing a memory address, or is that just saying that you're storing an int as a hexadecimal value?
Are you talking about this guy right here?
Just like the definition.
This guy holds the address.
Does it have to?
It holds the address of an integer, but that's going to mean something to us in a few minutes. Doesn't mean anything yet. So for right now, when you create anything, any known type with a little star after it, we're holding a memory address. We're holding something that looks like that. Okay, regardless of what the type was, int, char, whatever. All right. The reason chars behaved funny is somewhere in our computer we have an actual ASCII table, and it saw it was type char, so it resolved what was there to the actual letter. We could have forced it to do it, but for the quick example, I needed this. These guys are both integer types, but they definitely have different sizes, right? 4 bytes, 2 bytes, memory address looks the same-ish, right? Just like all the houses on the street all have the same kinds of memory addresses, street addresses, but the houses that are built there might be very different sizes. Okay. So having said that, let me dump this guy for a second. If I want to create a variable that knows how to hold the address portion of something, not the value. The value is being stored. The value is at that house, right? If I give you the address to my house, you can travel there and see my house, right? You could find the value. So given an address of a house, you can go and physically see the house. Make sense? If I give the address of an integer, you can go into computer's memory and find that integer, provided you have tools to walk through memory, and we do here. That's what we're introducing. But if I tell you where you can find the integer, you can go into memory and actually get the integer that lives there. Okay, so in this case, let's use your example. We have the integer 1000. Right here, I'm telling, this is how human beings solve problems, memory, asking questions, repetition. We are creating a variable. I'm creating a storage location in my computer to hold the number 1000, and I'm storing it inside of a variable named A. All right. And I've dictated, because it's a strongly typed language, that this guy is an int. which means I need 4 bytes of data. I need a piece of land that's 4 bytes big to hold my integer. I might not take up all that land. Okay, if you want to pull this into real life again, you might buy 4 acres of land, but you don't have to fill the entire 4 acres with your house. It's a big house. That's like something that like Boeing would buy for building jets. Actually, or Tesla with their gigafactories. Yeah, that kind of footprint would be in the acres. But so the size of the land that you have does not dictate the size of your house. It does dictate the maximum size of the house. Make sense? And it also doesn't even mean there's value there. In real life, can we buy a plot of land and just not build a house there? Sure. Okay. Now, that might not be all that useful in our programming world, but it works the same way. Where we're going to store something and the thing that's stored there are only related in the maximum size that it can be. Go ahead. Plus or minus, well, 4 bytes is 32 bits because a byte is 8 bits. So 4 times 8 is 32. So that would be plus or minus 2 to the 31st power. Because we use one of those bits for sign, for positive or negative. So 2 to the 31st power is roughly 2.1 billion. 2.147 billion. And we have plus or minus that. So if I have 4 bytes, I know that the maximum size house that can be built on a 4 byte plot of land is, especially since I can hold negative numbers, the maximum positive value that can be stored there is 2.147 billion. Any bigger than that, I need more land. I'm dumping over into the neighbor's land and they're going to probably be pissed. Make sense? But keep in mind that just because you've created a variable in this case of type int, which is going to tell the operating system, I need 4 bytes of land, because I might store something up to 4 bytes in there. It's going to give you 4 bytes of land, but it does not dictate that you have to fill that land completely. It just says, look, here's your land. You put what you want there, but you stay inside the fences. Make some sense? Okay, so very similar to real life. It just gets, I don't know, intimidating when we get into the computer world of it. So we would all agree that 1,000 is nowhere near the extremes of an int. It's not close to negative 2.1 billion. It's not close to positive 2.1 billion. It's very comfortably in the middle. And if we really looked at it, it's probably the equivalent of, like, I don't know, putting a cardboard box in the middle of a 4-acre piece of land. I mean, we're using a very tiny piece of, go ahead. What's this?
You get out of concrete.
Oh, so should we send around the collection plate? You gonna bribe me for it?
Oh, okay.
I only give you assignments when we actually have a skill that I want you to drill, and we likely won't get to what I want you to drill next today, but you probably will have homework over the weekend. Yeah. I don't give busy work. I mean, every time I give homework assignments is because I want you to drill something. I mean, you're just complaining about the 5 hours you had to throw at it. 5. I wish it was 5. I get where you're coming from. I promise you, I don't just arbitrarily give homework assignments. Because trust me, this semester I'm teaching 15 classes. I don't want to grade more homework assignments than I have to grade. Most of them are in our grad program. But yeah, which has its own challenges. They like to work in groups on final exams. We have one of the classes just ended this last week because they're 8-week classes, the grad classes. I was grading the final exams, and it was really hilarious hilarious in a really sad way, where you would have, so one of the pods of cheaters were like 11 students. And I imagine they were all sitting in the same room working on the exam at the same time. It was on Blackboard. Now, I grade everything with names off, but with exams, my exams have 10 questions. I grade them one question at a time. So I had 44 question number 3s. Answer, 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 answer. And it shows them in the order in which they were submitted. So all these students, these 11 students must have submitted it, within 15 seconds of each other. So I have 11 identical answers just laid out for me for every single question on the test, even the easy ones. And I had a group of 5, and that's a whole nother thing of the business of higher education. Long answer is I should have. Short answer is I didn't, but I gave them arbitrarily low enough grades that they're going to have to not cheat in the future, and we'll have to fix the grade they got with an A plus another B plus in order to graduate. Because you need to have a 3.0 to get a master's degree. So you fix it that way while keeping them in the program. It's not the most ethical thing you can do, but tell you what, if you fail them, they'll drop, they'll go to some other school that'll give them the degree down the street. That's the nasty underbelly of higher ed. But you give them low enough grade, and then you don't write them a letter of recommendation. You've mostly solved the problem while still collecting their tuition. I mean, it's the unfortunate truth, right? This is just business, and as faculty, we have to figure out, well, what can we do to benefit the business while not like screwing future employers? Because if everybody that's dumping out of here is just getting random product from Concordia, then you're in trouble. Go ahead. Oh no, I said no, they definitely don't think they got away with it. And we've had plenty of discussions. Part of this is somewhat of a cultural thing. A lot of our grad students are from India. And I've traveled over there to recruit a lot of these guys. So I know a lot of them from like meeting their parents and stuff in India. And they're not bad people, but they do whatever it takes to get out of India to get into the United States. And a lot of times what they've claimed their undergrad degree is in and stuff like that is falsified documents. I mean, if I lived over there, I maybe would do the same thing, do whatever it takes to get out. So I can't blame them, but they have complications in life that are bigger than just school, but I can only judge them on what their stuff for school looks like. It's a very interesting business. Okay, so back to this for last couple minutes. So I really want to drive that point home. If we're thinking about it in real life, the street address of a house does not tell us about how big the house is that's there. But if we looked at a list of land lots, the street address could tell us what's the maximum size of that house, right? If right now I'm looking at a plot of land here in Mequon to possibly build a place. And, there were 7 lots to choose from, and the lots are all different sizes. So they went from a half acre all the way up to almost 2 acres. So, the street address of all those are right next to each other, are going to be very, very, very similar street addresses, just with different numbers in front of it, right? But that doesn't dictate how big the house that will be that's on that plot of land. So we want to think about that the same way here. But when I do say I want to, because again, this just goes back to I want to remember something. How do we remember things in C++? We create variables to remember things. So I'm going to create a variable here called a_address. I can name it whatever I want, but I named it a_address because I'm going to be storing the address of A in it. Okay. But the type of that variable is an int pointer. That's how you would read this, int pointer with that star. You will sometimes see a space there, which is still legal. I hate that. I don't like the disconnect of those. I'm not going to mark off for it if it's right, but I think it's bad programming practice. The type of this is an int star. It's an int pointer. What does that tell me? It tells me that this variable is going to hold a memory address. Specifically, the thing that lives at that memory address will be an integer. I don't know. It doesn't tell me though how big that integer will be. Okay. I just know that land is zoned for integers. we think about it again in real life. You have land zoned for residential, for commercial, for farming, all sorts of different things. So this land that I've gotten here is zoned for integers. Therefore, what's there will be an integer of some type. Okay, eventually. It might just be land that has nothing built on it yet. But what is there? This guy does dictate the kind of thing I should expect to find there. And because we know in our programming language, in C++, Java, C#, kind of, they're all very, very, very similar. I know how big an int is. An int in all those languages is 32 bits. Or similarly, you can say it 4 bytes. Those are the same value, just one's given in bits, one's given in bytes. Okay, that's the amount of land associated there. Go ahead. Well, in this case, no. In this case, the land was actually created right here. Well, actually, the answer is yes, but let me give it more detail. I actually created the land right here. When I wanted to store the number 1000, the computer created a place in memory for me to put that 1000. I had to store it somewhere. So the computer created that, didn't tell me where it put it, just say, look, I stored it for you. You have a variable named A. When you need that value, just read the value of A and you'll get your 1000. Okay. Don't worry about where I put it. I'll look it up when you need it. Right here, I'm creating a second storage location. Okay, what does that mean? There's going to be a location in memory where my variable called A_address lives. So after these 2 lines, there are 2 separate locations in memory. One location is a plot of land big enough for holding an int. The other location is a plot of land big enough for holding a memory address. However big a memory address is in that operating system. Okay, if we're on a 64-bit operating system, chances are a memory address is going to be 8 bytes, which then becomes kind of an interesting thing. A 64-bit memory address is actually larger than an int. And this is kind of where that whole pass by value versus pass by address thing comes in. Which is cheaper? Which is more efficient? Is it more efficient for me to hand you a 4-byte integer? Or is it more efficient for me to hand you an 8-byte memory address where you can go and find that integer? Make sense, the difference? Okay. If I hand you the integer, I'm giving you a copy of it. Here is a 4-byte copy of something I have. As opposed, and any changes you make, you're doing to the copy. As opposed to me handing you 8 bytes, twice as much data, but not a huge amount of data, but twice as much. Here's 8 bytes. This will tell you where you can go and look. It's like a treasure hunt. Okay. This is where you can go and look to find that value. But now if you go there and you start making changes, those changes are permanent because you've made changes to the original place. Make sense? So 2 different, I know we're out of time here. Let me just finish the thought. 2 different locations are being created here because I'm creating 2 variables. One of these variables is a plot of land that's big enough to hold something of integer type. The other one is a plot of land big enough of holding something of memory address type, however big that is on that operating system. Okay. But in this case, we've made the connection where we have stored in this memory location, in this variable, the address of, because this guy is big enough to hold an address, but I've put in there a specific address. What address? The address of this guy. Okay. All right. We'll talk a lot more about this on Thursday. Questions, comments, concerns, bribes. Of the pointer, of the structs. Pass it the memory address of the structs, do whatever we want with them then, and now it had side effect because we changed in real memory. And we'll do that next time. Okay. Go ahead. I'll keep the thing recording. I know some of you got to run, but we're already over. But
You saying so the address has an address?
yeah, variables have size. So yeah, in order for the computer to remember something, in this case, the computer's remembering 2 separate things. It's remembering A and it's remembering A_address. it has to create a little place in memory to store the things we want to remember.
So you're kind of doing two things right here. First, designating size of, or like the maximum
Yep.
size.
Yep.
By saying int,
Yeah, how big is my plot of land?
and then.
How am I gonna reference it? And what do I want to build there? This is the house. I'm building a house of size 1,000 on something that could hold a house of size 2.1 billion.
And you could just say int a semicolon. And-
Yeah, you could
and
do
that-
this, and that's like buying the land. You have an acre of land, but you haven't put anything there yet. Or in this case, you have 4 bytes of land with no actual value stored there, but it's ready for you to build. Make some sense?
And you could do a whole bunch of stuff with a without even giving it a value. It's just.
Well, at some point,
Like
it's
you could change the location of the plot of land.
well, once you've defined it here, the operating system is going to give you a place to put this guy. You wouldn't be
But
able to
if you
move
wanna
it.
Assign it a different address.
You could assign it a different address and then just abandon the old address and let the operating system take care of it. This is going to be something with like deleting memory after you've created it. But you're right. You could say, look, I don't care about the land you created me before. I'm just going to abandon it and I'm going to focus on this new land that I set it equal to.
Are we doing that right now by assigning addresses? Like-
No, because what I'm doing here is this asks the operating system to create a bucket. I'm putting something there. This says create another place to remember something, but what I'm going to remember is the address of
Oh, it's
this
just-
guy.
Oh, it's just information. about the
information. Yeah,
address.
we're storing multiple things. It's like having a Post-it note with a street address written on it.
It's not actually changing
No.
anything in the street. It's
Nope.
just giving-
Correct.
Thank you.
Yep.
I know this is gonna sound kind of stupid, but for the homework yesterday,